All right, let's dive in. Today we're tackling algorithms, specifically QuickSort and order selection.
Oh, these are good ones.
I know, right? They sound
Yeah.
kind of dry, but I promise this is going to be anything but.
Hmm.
Because, like, QuickSort, it's literally everywhere.
Yeah, that's true.
Like, think about it. Sorting contacts on your phone
Hmm.
or, like, huge data sets in some complex data analysis.
Mm.
It's QuickSort behind the scenes.
Absolutely. It's a fundamental algorithm, and
Yeah.
understanding it, I think it gives you a real edge.
I agree. It's like you start to see how computers actually think, you know?
Yeah.
So to break it down for today, we've got two key problems we're looking at: sorting and order selection.
Right.
Sorting, like we all know that one, right?
To classic.
You got a list of things, you need them in order. It can be smallest to largest, A to Z, whatever. How do you do that efficiently? That's the question.
Exactly. Efficiency is key when you're dealing with huge amounts of data.
Totally. And then we've got order selection, which is a little different. Like imagine you need to find say, the third smallest number in a list.
Oh, interesting.
Right. But you don't want to sort the whole list to do it. Can you find that specific element quickly?
And that's a really common problem, actually. Think about finding the median price of a list of products.
Oh, that's a good one, yeah.
Or like the 50th fastest runner in a marathon. Order selection is all about finding that specific element.
Exactly. So we're going to cover both the what's and the why,
Mhm.
try and make these complex concepts clear, make them relatable, all that good stuff.
We'll break it down.
Okay, let's start with QuickSort. This is one everyone keeps talking about. I've heard it uses this divide and conquer strategy, which sounds super epic.
It really does live up to the hype.
Okay, good.
Imagine like you have this huge stack of papers to sort.
Okay, got it.
Right. Instead of trying to sort the whole thing at once, what if you divided it into smaller piles?
Okay, makes sense.
Maybe by category or something. Then you sort those smaller piles and then, merge them back together.
Oh, that's a good visual, yeah.
It's kind of like what QuickSort does, breaking down the problem.
So it's like instead of tackling the whole monster, you're taking it down piece by piece.
Exactly.
Okay, I kind of get the big picture. But how does QuickSort actually divide that initial list? How does it choose where to make the cuts?
The secret is something called partitioning. So QuickSort picks a special element, a pivot,
Okay.
and it uses that pivot to rearrange the list. Everything smaller than the pivot goes to one side, and everything larger goes to the other.
So it's like using this one element to organize the whole thing.
Yeah, exactly. The pivot is like the dividing line.
That's pretty clever.
Yeah.
But how does it pick that all-important pivot? Does it just choose the first element or?
Well, that's a great question. And the choice of pivot can actually make a big difference in how fast QuickSort runs.
Oh, really?
In the best case scenario, the pivot splits the list perfectly in half, leading to really, really fast performance. We call O of n log n in computer science terms.
O of n log n. That sounds impressive, but I'm not going to lie, I'm not a computer science whiz.
Fair enough. So let's make it more practical. Imagine you're sorting 1,000,000 records.
Okay, huge data set.
Right. With this ideal efficiency, the O of n log n, QuickSort might take, I don't know, a few seconds.
Wow, that's fast.
But then there's the but.
There's always a but, right. Okay, so what happens when the pivot isn't so perfect?
Yeah, so in the worst case scenario, if the pivot ends up at the very beginning or end of a sublist, QuickSort can slow down to a crawl. We're talking potentially hours to sort that same 1,000,000 records.
Hours. That's a huge difference. What causes it to be that slow?
Yeah, that's represented by O of n squared.
O of n squared. Okay, so that's the bad one.
It's not ideal.
Got it. So what if, like, we're dealing with data that's already almost sorted? Wouldn't that trigger that worst case scenario?
That's a really good point, and that's why most implementations of QuickSort actually use what's called randomized QuickSort.
Randomized QuickSort. Okay, so what's that do?
Basically, it either shuffles the list before starting or picks a random pivot each time.
So it's like preventing the data from being too organized.
Exactly. It makes that worst case scenario much, much less likely.
So it's like shuffling a deck of cards before you start sorting. Okay, that makes sense. But let's shift gears a bit. Let's talk about order selection. Remember, this is about finding that specific element, like we talked about, without sorting the whole thing.
Right. A very specific task.
Exactly. So how do we approach that?
One common way is using a special data structure called a heap.
A heap. Okay, tell me about heaps.
So a heap is like a tree-like structure that's organized so you can efficiently grab the smallest or largest element.
Okay.
We have two types, a min heap for the smallest element and a max heap for the largest.
So if we needed like the median value, we could use a min heap to quickly find that.
You could, but using a whole heap might be a bit overkill if you just need one specific element.
Oh, okay, so it's like bringing out the big guns when a smaller tool would do the job.
You could say that. There's another approach that actually leverages the power of, you guessed it, QuickSort.
Wait, really? QuickSort can be used for order selection, too.
Absolutely, and it's actually very clever how it does it.
All right, I'm hooked. Tell me more.
So instead of sorting both sides of the partition, remember the partitioning we talked about earlier?
Yeah, with the pivot and all that.
Right, so we only focus on the side that contains the element we need. It's a bit like a detective eliminating suspects until they find the one they're looking for.
So we're strategically choosing which parts to sort and which to ignore.
Exactly. It makes the process much more efficient.
Smart. But is there a catch to this efficiency?
Well, there's always a trade-off, right?
Yeah.
You can choose methods that give you an approximate answer really fast, but they might not be 100% accurate.
Oh, interesting. So sometimes it's okay to have a little wiggle room in the answer.
Exactly. It depends on what you need.
Makes sense.
Yeah.
You mentioned a way to guarantee good performance even in those worst-case scenarios, the median of medians approach.
Yeah, that one's a bit of a head-scratcher, but we'll dive into that in the next part of our deep dive. It's a whole other level of cleverness.
Sounds intriguing. I'm ready for the challenge.
It's going to be fun.
All right, welcome back to our deep dive into quicksort and order selection. Before we tackle that median of medians thing you mentioned, I'm kind of curious, what makes these algorithms so important in the real world?
Yeah, good question. I mean, most people aren't like coding them up every day.
Right, exactly. But why should we care about them?
Well, even if we don't see them, algorithms are running behind the scenes, like constantly. Think about any time you search for something online,
Oh, yeah, for sure.
or like book a ride, or even get a personalized recommendation. It's algorithms doing all the heavy lifting.
So basically, understanding these things, even just a little, helps us appreciate, like, the complexity behind all that stuff we take for granted.
Absolutely. Like you start to see the magic behind the curtain, so to speak.
I like that analogy. Speaking of magic, let's circle back to QuickSort for a sec. We talked about those best case and worst case scenarios, but what about the average case? Like, in real life, how does it usually perform?
Right, yeah. With that randomized quicksort, it seems like those worst case situations are pretty rare, so what can we expect most of the time? Well, the good news is that, on average, quicksort is super efficient. In fact, its average performance is also O of n log n, just like the best case.
Wait, so we've got another O of n log n.
You got it.
Remind me again why that's so good.
Think of it this way. As the size of your data doubles, the time it takes to sort only increases a little bit more than double.
Okay.
That's way better than, say, O of n squared, where doubling the data size could, like, quadruple the processing time.
Oh, okay, that makes sense. But how do we know that QuickSort performs that well on average? Like, the math behind that seems pretty intense.
Yeah, analyzing that average case complexity does involve some heavy-duty math, but the basic idea is this. With that random pivot selection, it's really likely that most of those pivots will end up dividing the list into roughly equal parts.
Oh, so it's like flipping a coin. You might get a few heads in a row, but over many flips, it'll average out to about 50-50.
That's a great analogy.
Thanks.
And since those good pivot splits help us get closer to a sorted list quickly, even if we get a few bad ones, it doesn't mess up the whole thing.
So it's like the randomness is actually what makes it reliable.
Exactly. That's why randomized quicksort is used so widely in everything from databases to search engines.
It's like the unsung hero of the digital world.
For sure.
This makes me think about algorithm design in general. Like, it's not just about finding the fastest solution. It's also about balancing speed with, like, how reliable it is and even how much memory it uses.
Yeah, it's a constant balancing act. Algorithm designers are kind of like engineers, right? They got to consider all these trade-offs and limitations to find the best solution for each problem.
That's a good point. Okay, I think I'm ready to tackle that median of medians algorithm you mentioned, the one that guarantees good performance for order selection, even in those worst-case situations.
Right, let's do it. So, the key to fast order selection is finding a good pivot for that partitioning step.
Right, we talked about that.
And the median of medians approach, well, it's all about consistently finding a pivot that splits the list pretty evenly.
Okay, I remember you saying something about dividing the list into groups, but why is that important?
Imagine you divide your list into groups of 5 elements each.
Okay, 5 elements per group.
That's a sweet spot for this algorithm because each group is small enough to be sorted really quickly.
Okay, I see. Yeah.
But it's also big enough to give us a decent idea of how the data is spread out.
So we've got these groups of 5. What's next?
Well, we find the median of each of those groups.
Uh-huh.
We can use any sorting algorithm. It doesn't really matter since they're so small.
So we have a bunch of medians. Then what?
This is where it gets fun. We find the median of all those medians, and that becomes our pivot for partitioning the whole list.
Wow, a median of medians. That's a lot of medians. But how does that guarantee that we'll get a good pivot?
Well, think about it. At least half of our groups have medians that are smaller than or equal to the pivot we chose. And within those groups, at least half of their elements are also smaller than or equal to their medians.
Okay, starting to see it.
So that's a big chunk of the list that's guaranteed to be smaller than our pivot.
So no matter what, we're basically ensuring that the pivot splits things up pretty evenly.
Exactly. That's the beauty of the median of medians approach. No matter how tricky the data is, it finds a good pivot and avoids those worst-case scenarios.
I see the appeal, but you did say it's kind of hard to actually implement. Is it really used in practice, or is it more of a theoretical thing?
It's definitely more complex. To be honest, randomized QuickSort usually does the job just fine. But knowing this algorithm exists kind of shows you how far you can push for the best possible solution, even in the toughest cases.
It's like the ultimate backup plan.
Exactly.
This deep dive is turning into quite the algorithmic adventure. We've explored QuickSort, order selection, and even tackled the median of medians. And there's still more to come.
Stay tuned for the final part of our deep dive, where we'll wrap things up and explore some final thoughts about this fascinating world of algorithms.
All right, welcome back to the final part of our deep dive. We've covered some pretty complex stuff, but before we wrap things up, I wanted to circle back to something you mentioned earlier. Those approximate methods for order selection. You know, the ones that give a quick estimate but aren't always perfect.
Yeah. Those are kind of like the shortcuts.
Okay, shortcuts. I like that.
They sacrifice a little bit of accuracy, but they make things so much faster, which can be a big deal when you're working with tons of data.
So how do they actually work? Do they just, pick a random element and hope for the best?
Not quite. Imagine you take the whole range of values in your data and you divide it into smaller intervals, like buckets.
Buckets, okay. Got it.
And then you go through the data set and count how many elements fall into each bucket.
Okay.
You're not actually keeping track of the exact values, just how many are in each range.
So you're getting a rough idea of how the data is spread out without getting bogged down in the specifics.
Exactly. It's like getting a bird's eye view. And once you have that, you can estimate where the naive element would fall based on which bucket it lands in.
Oh, I see. So if we were looking for the median, we'd find the bucket that holds the middle element, even if we don't know the exact value.
You got it. And the best part is, counting elements in buckets is way faster than sorting everything. Of course, the more buckets you have, the more accurate your estimate will be, but it also takes a bit longer.
So it's that classic trade-off, speed versus accuracy. Sounds like these approximate methods are super useful when you just need a quick idea of where things stand without needing to be super precise.
Definitely. They're used a lot in data analysis, like when you're just trying to get a feel for the data before you do any serious number crunching.
This whole deep dive has been a wild ride. We've gone from basic sorting to complex algorithms and even approximation techniques. I feel like I've learned a ton about how computers do their thing.
It's been fun exploring it all with you. I hope our listeners are walking away with a new appreciation for the cleverness and, the elegance of these algorithms that power so much of our world.
Absolutely. So as we wrap things up, I want to leave our listeners with this thought. We've seen how different algorithms have their strengths and weaknesses, and how picking the right one depends on the specific problem you're trying to solve. It's like having a toolbox full of tools, each one perfect for a particular job. So as you keep exploring the world of algorithms, remember that there's no one best algorithm. It's all about understanding the trade-offs and making smart choices based on what you need to accomplish. Thanks for joining us on The Deep Dive.